So in chapter 9, we're going to kind of take a little bit of a detour, and we're going to kind of come back to things relating to integrals. When we do integrals, we're adding stuff together. And in the last section, we added stuff together like forever. We did integrals that went to infinity, and which is kind of a strange concept. So we're going to be talking about adding a lot of stuff together in this chapter. And as we get to the end, we're going to look at ways of taking some functions that may or may not be easy to do calculus with and rewriting them in other formats. For example, sometimes we can take trig functions and write them to make them look like a polynomial. Polynomials are easy to do calculus with. If we have a polynomial and we want to take the derivative, we just use the power rule on every term. If we want to integrate, we make everything to the one bigger power over that power. But some trig functions, some of the other transcendental functions, e to the x, natural log, log, sometimes those are a little bit strange when we do different calculus things with. So before we get into adding a lot of stuff, the first section kind of sets a lot of this up, and it's talking about sequences. Now, I'm sure you probably run across sequences at some time or the other, but let's define what a sequence is to begin with. It's just a function, but for that function, the domain is not just any number, it's positive integers. So, for example, it might be that a sub n is 2/5 to the n power. And we're not just going to evaluate that for any number. We're only going to evaluate it for positive integers. So a sub 1, which is considered the first part of the sequence, the first term in the sequence, would be 2/5 to the first power, which is, of course, just 2/5. A sub 2 would be 2/5 to the second power. Of course, remember when we raise a fraction to a power, we raise the numerator to the power and the denominator to the power. The third term in the sequence would be from taking 2/5 and raising it to the third power. So 2 to the third over 5 to the third. And of course, we could list lots and lots and lots of terms in that sequence. When we did Newton's method, Newton's method, in a sense, was a sequence, but remember, it went like this. I think I have my prime backwards on the top. Remember, we kind of picked a starting point, and then the next estimate was dependent upon our first number. That's known as a recursively defined function. So sometimes we will have a sequence that is defined recursively. What do I mean by that? Let's look at an example. Let's suppose we have a sequence where we say the first value in the sequence is 25, and then all future values in our sequence come from taking a previous value and subtracting 5. So if the first value in the sequence is 25, then the second value in the sequence comes from taking the first value minus 5. Now, for recursively defined sequences, we have to be told the starting point, since all other terms in the sequence are defined based on the previous step. So we have to know what that previous step is. If we never know the starting point, we can't tell you what the following values are. So for the second term in the sequence, it's the first term minus 5, so 25 minus 5, so 20. The third term in the sequence is the second term minus 5, so 20 minus 5, 15. The fourth term in the sequence is the third term minus 5, so 15 minus 5. And we would just keep on doing that for however many terms of that sequence we wanted to list. We can look at some other here's a sequence. Let's see. Here's a sequence. Sometimes we're told what the function is that generates our sequence. So like on the previous two, we were given some formula, whether it was a direct formula, a function that told us the terms of the sequence. If I say, hey, what is the fifth term in the sequence, I plug a 5 in for n. If I want to know the seventh term in the sequence, I plug a 7 in for n. Or if it's a recursively defined sequence where I tell you how to get from one term of the sequence to the next, and I just have to know a starting point. So often we have a formula for our sequence. Sometimes we're just told, okay, here's a list of numbers that have a pattern. So like on the first one, y'all see the pattern? The top number stays the same. The bottom number is getting bigger by 1. So it's, yeah. That's right. If we call this the first, the second, third, fourth, fifth term of the sequence, then we could write a formula for that one. The numerator is always 1. The denominator is always 1 more than n. So yeah, that would be a formula for that first sequence. All right, if we look at this one, and n is 1, 2, 3, 4, 5, and so forth, what would be a formula for that sequence? Yeah, notice the top is 1, the bottom is just the square of n. So sometimes we'll have that exercise. Here's a sequence of numbers. Find a formula. How do you get from one value to the next? Sometimes we will alternate signs. If we alternate signs, that's normally going to involve -1 to a power. Because think about it, if we raise -1 to integer powers, when we have -1 to the first, we get -1. But when we have -1 to an even power, we get +1. And -1 to the third power, we're back to a negative. So if we're alternating signs, somewhere in there we need a -1 to a power. Now, notice when n was 1, we got -1. When n is even, we got a positive. Is that the sign relationship we have on this one? When we had an odd n, yeah, we have a negative value. So for this one, we would have -1 to the n. That would give us our changes in signs. But what if Let's write another one. And let's say our signs are positive, negative, positive, negative, positive. So first of all, to generate just the numbers, on bottom, let's see, if n equals 1, 2, 3, 4, and this is supposed to be 10. 5, how do you get the denominators from n? What's the relationship from n in each denominator? Yeah, that's one way to do it. If you take this one plus that, you get, no. They go up each time by how much? By 2. So multiply, they're going up by a factor of 2. Yeah. They each time go up by a factor of 2. So 2 times whatever n is. When n is 3, we got 6 on bottom. When n is 2, we got 4 on bottom. When n is 1, we got 2. Now, if we just do negative 1 to the n on top, let's see if that works. If we let n be 1, we get the right number on bottom. But what's negative 1 to the first power? Oh, we don't need a negative 1. We need a positive 1. They are alternating every other one, but we don't need to start with a negative 1. So how do we... Well, that's a good thought. But if we put the negative on the outside, then every one of them is going to be negative. That's still going to do essentially the same thing that he said. It's going to make every one. Aren't we basically shifted over 1? If we... With this one, we're getting negative, positive, negative, positive, negative, positive. We need it to be shifted over so that we have positive, negative, positive, negative, positive, negative. Well, how can we do that? We could just add 1. Notice if I put a plus 1 here, when n is 1, what's 1 plus 1? 2. Isn't negative 1 squared now positive? Let's try another one. Now, let's say, how about when n is 4? If we put 4 for n, now our exponent, instead of being an even number, is an odd number. What's an odd amount of negatives? Negative. So that do it. So if we need to alternate signs, we need either a negative 1 to the n or a negative 1 to the n plus 1. It just depends on, do we need to start with an odd or start with an even? And instead of memorizing, well, which one starts negative, which one starts positive, just list them both out and say, okay, if n equals 1, what's that one going to be? That one's going to be negative. What's this one going to be? Well, negative 1 to the second, that one's going to be positive. So then you can kind of figure out which one you need. Is it negative 1 to the n, negative 1 to the n plus 1? So that's kind of an introduction to what a sequence is, but we want to know more than just what is a sequence. We often want to find out, well, what if we take the limit of a sequence? So the limit of a sequence is just, what is that sequence going to approach? What value is our sequence going to get close to as we let it go on forever and ever and ever? Now, some of the ones that we've already looked at. If we look at that one, if we keep on going, what's happening to these fractions if the numerator stays 1 and the denominator is getting bigger and bigger and bigger? What's that going to go to? 0. That sequence was 1 over n plus 1. Well, guess what? Just like with a function, you can take the limit of a sequence as well. If you let n go to infinity, 1 over an infinitely large number is 0. So if we get an answer for this, that sequence is said to converge. So, and the limit of that sequence is we call L. Let's see. Limits, the properties for limits of sequence is basically the same for properties of limits of regular functions. They give us some examples. If we have the sequence given by 3 plus -1 to the n, let's look at what the limit of that sequence is. And like in the last section, when we were looking at improper integrals, we said that the answer to that, we get a number, but we also say whether or not it converges or diverges. And we came back and explained that if for those improper integrals, as we got closer and closer to infinity, if we were approaching a specific value, then we said it converges. But if we either go to infinity or if we don't go to a specific value, then we say it diverges. So the same thing is going to be true of sequences. So let's look at the terms of this sequence. When n equals 1, what is -1 to the first? -1. So the first term of the sequence is going to be 3 minus 1, which is 2. When n is 2, -1 to the second power is +1, so we're going to get 4. When n is 3, we get -1 to the third, which is -1. When n is 4, we're going to have -1 to the fourth, which is +1. And is that ever going to stop doing that? No, it's going to go 2, 4, 2, 4, 2, 4. It's going to go on forever. So as n goes to infinity for that sequence, does that converge or diverge? Does it go to a particular value, or does it not go to a particular value? It diverges. We talked about an example of an improper integral earlier involving sine or cosine. If we let that go on forever, it's never going to settle on one number. It's going to bounce back and forth. You're going to have some positives and negatives, positives and negatives. That's kind of what's going on here. As our sequence continues, it's not settling in on a particular value. It's bouncing back and forth between lots of different values. So we say that that one diverges. Let's look at another one. Let's see whether or not this sequence converges. So if we just list some terms of this sequence, if we put in a 1, we have 1 over 1 minus 2. If we put in a 2, we have 2 over 1 minus 4. 3 over 1 minus 5. 4 over, I said 1 minus 5, 1 minus 6, which is minus 5. 1 minus 8 is negative 7. 1 minus 10 is negative 9. So that's what that sequence is. So if we let n go to infinity, if we just plug infinity in, we would have infinity on top, negative infinity on bottom. But that's indeterminate. What is a way that we can evaluate that limit? What is a new way that we've learned to evaluate that limit? Yeah, the hospital rule, L'Hopital's rule. If that's indeterminate, take the derivative of the top, take the derivative of the bottom, and then take the limit again. And if that limit exists, then that is our limit. Notice, to begin with, these terms are not really close to 1/2. But each term on bottom, the denominator, if you think about the absolute value, 11 is 1 more or 1 less than twice the top. 9 is 1 less than twice the top. If the top is 30, the denominator is going to be 1 less than twice the top. Twice the top is 60, so we would have 59 on bottom. Isn't that really pretty close to 1/2, but negative? That's what's going to happen. The farther our sequence goes, the closer and closer our fractions are to being negative 1/2. So we say that for this sequence, it converges, and that's what it converges to, negative 1/2. Let's look at another one. Let's just list some terms in this sequence. If we plug in a 1, we get 1 over 2 minus 1. If we plug in a 2, we get 2 squared over 2 to the second, so 4 minus 1. If we plug in a 3, we get 3 squared over 2 to the third minus 1. If we put a 4 in, 4 squared over 2 to the fourth minus 1. Let's do one more. If we put in a 5, we get 5 squared over 2 to the fifth minus 1. What do y'all think that's going to converge or diverge? Any guesses? Converge? That's a good guess. So let's see. Let's take the limit as n goes to infinity. Now, if we just plug infinity in, we get infinity on top. Infinity to a power is infinity. 2 to infinity is infinity minus 1. So that's indeterminate. That is indeterminate. So if that's indeterminate, let's use L'Hopital's rule. So take the derivative of the top, and then take the derivative of the bottom. Ooh, how do we take the derivative of 2 to the n? Remember that one? That's an a to the n. Remember, if we take the derivative of a to the n, that's natural log of the base times a to the n, and if there's a, and technically times the derivative of the exponent. Remember the derivative of e to a power is e to the power times the derivative of the exponent. This is just simply a different base. And when we have a base other than e, we pick up a natural log. So the derivative of 2 to a power is 2 to that power times the derivative of the exponent times natural log of the base. Isn't that still indeterminate? If we plug infinity in now, we get infinity on top, infinity on bottom. So guess what we need to do? Do it again. So if we take the derivative of the top this time, we get 2. Let's see, we have a natural log 2 on bottom already. And if we take the derivative of 2 to the n again, the derivative of 2 to the n is 2 to the n times the derivative of the exponent times natural log of the base. Now we could simplify all of that, but notice we have a constant on top, and if we let the denominator go to infinity, what is that going to go to? 0. That's going to go to 0. So does that converge or diverge? That converges. All right. Let's see. Let's remind ourselves of what this notation means. There will be some sequences involving factorials, and what a factorial means is we take that number and multiply it times all integers between that number and 1. So 8 factorial means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Those can get big in a hurry because each time the factorial number gets bigger, we're increasing by a multiple of whatever that number is. So just like exponential numbers grow quickly, and numbers like that grow fairly quickly, factorials grow really fast because each time that increases, we're picking up a multiple, but each time the multiple is getting bigger and bigger and bigger and bigger. One thing to note is that 1 factorial is just 1. A factorial that kind of hard to understand, but it's kind of a definition. 0 factorial, just remember that it's 1. All other factorials by definition means multiply every integer from 1 up to that number. But if you're already at 0, how do you go from 1 up to 0? Well, you don't go up to 0. So just recall that 0 factorial is 1. All right. I'm going to mention the next theorem. The next theorem is what's known as the squeeze theorem. And we dealt with the squeeze theorem back when we were talking about limits in general. So they say if the limit is n goes to infinity of the sequence A is L, and if the limit of the sequence is n goes to infinity of the sequence B, if that's the same thing. So basically, if you have 2 sequences that have the same limit, and let's suppose we have another sequence, and that third sequence is always between the first 2 sequences. Then guess what? If this sequence is between those 2, and we know what those 2 go to, that other one has to go to the same thing because it's squished right in between it. So, for example, let's look at a picture. Let's suppose we have a sequence that is doing this. So we're going to call that sequence C. If we have another sequence that's always bigger than that one, and then a sequence that's always smaller than that one, if, let's see, let's call this one A and this one B. I may have written it the other way earlier. So if C is always less than or equal to A, and if C is always bigger than or equal to B, and if A and B converge to the same thing, if we know what A and B both converge to, if C is always in between them, it's like a sandwich, it's like a vice we're squeezing down. These are getting closer to each other, these are getting closer to each other, and the blue one has to be in between them. So if the red one and the green one are going to a certain number, and the blue one is in between them, guess what? It has to be going to that same number. Now that turns out to be kind of useful because sometimes we have sequences that are not always easy to determine what they converge to or if they converge. So, for example, that one. If we took that sequence, it might be hard to figure out what that is going to approach. But if we can find a sequence it doesn't necessarily initially have to be bigger, but if there reaches a point where our new sequence is either the same or bigger, and then if we find another sequence that our new sequence is always the same or smaller, if that one's in between those two sequences and we know that those go to a particular value, then that will let us know what the one that we're unsure about goes to. So let's compare this one let's compare it to that one and that one. So let's compare n factorial and 2 to the n. N factorial means 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. 2 to the n means 2 times 2 times 2 times 2 times 2 times 2. For a while, this one is going to be bigger. But is 2 to the n always going to be bigger? after a while, notice out here, in this step, we're multiplying by 2 here, but we're multiplying by 4 there. Out here, we're only multiplying by 2 when we go to the next term, but we're multiplying by 7 here. Imagine when we're out here and we're multiplying by like 100 times 101 and so forth. Well, we're only multiplying by 2 out here. So in terms of growth, which of those is growing faster as n gets bigger? Is n factorial growing faster, or is 2 to the n going to grow faster? That one's going to grow faster. To begin with, this one is bigger for the first 3 or so terms, but after a while, this one is going to get bigger faster and faster and faster. Well, if this is bigger than this, why is that bigger than that? If n factorial is bigger, why is this fraction bigger? Right. If the numerators are the same, if I have 2 fractions and they have the same numerator, the one with the bigger denominator is the smaller amount. The one with the smaller denominator is the bigger amount. Is it 1/2 more than 1/5? Yeah. So if I have if the numerators are the same number, if the bottom number is bigger, then that's a smaller amount. So if we look here, that denominator is bigger, so that means this fraction is smaller than that one. Now, if we take the opposite, we won't go into all the detail, but this one is bigger than that one. But if we take the opposite of both of them, then all of a sudden it turns around. Remember, when you multiply an inequality by a negative number, when you multiply an inequality by a negative number, what do you have to do to the inequality symbol? You have to flip it. So when these two were positive, 1 over 2n was bigger. But if we take it and multiply it, let me erase. That one was bigger than 1 over n factorial. If we multiply both of those by a negative, it flips the inequality symbol. So negative 1 over 2n, that's going to be smaller than the middle one. The tricky thing about the middle one is it alternates signs. Sometimes it's positive, sometimes it's negative. In this squeeze, when 1 over 2 to the n is negative, that's always going to be smaller than our n factorial. When it's positive, it's always going to be bigger. And this has an extra term. So that one is always in the middle. Well, if we look at the one on the left, when n goes to infinity, what does the one on the left go to? If the denominator is going to infinity and the numerator is staying a constant, that approaches 0. Well, guess what? The other one, as n goes to infinity, that one also goes to 0. We have shown that our sequence is always in between that one and that one. If those both go to 0, then what does that one have to go to? It has to go to 0 also, because something smaller than it and something bigger than it, they converge to 0. This is always slap dab in the middle of them, so it has to go to the same thing as well. That's kind of a last resort for showing convergence, is finding things that are bigger and then smaller than that one, because sometimes it is hard to find. If that's our sequence, what is something that's bigger than that? And then what is something that's smaller than that converges to the same number as the bigger one? So that can be a little bit tricky. One of the thing that made this really tricky is that -1 to the n business. It was alternating signs back and forth. If it was just that sequence, if we let n go to infinity, what would that go to? That would go to 0. The top is constant. The bottom is getting bigger and bigger and bigger and bigger. So that is going to 0. But when we were bouncing back and forth, that was harder to see. Well, what are we converging to? We had a sequence earlier that bounced back and forth, back and forth, like this, and it never did converge to anything. So sometimes when sequences bounce back and forth, they don't go to anything, but in this previous case, they did. So our next theorem is going to be called the absolute value theorem. And it's going to help us with problems like that last one. They say if we have a sequence a sub n, if the limit as n goes to infinity of the absolute value of that sequence, if that limit, when we take the absolute value, if that goes to 0, then the sequence itself has to be going to 0. So let's see what we mean by that. Let's go back to this previous example. So here is our sequence. They say, let's take the absolute value of that sequence and see what it goes to. What part is making the sign negative sometimes? That part. Isn't this one here always positive? N factorial is always positive. So the only part of that formula that causes us to be negative at some point is that. So if we take the absolute value, we're just going to make that go away. If we take the absolute value of -1 to the n times 1 over n factorial, when you have a product, you can take their absolute value separately. So the absolute value of -1 or 1, that's just going to be 1. That's positive anyway, so there's no need to have absolute values on it. So for these absolute value theorem problems, if we have a part of our sequence that is alternating -1, when we take the absolute value, we're just going to make that part go away. So what this theorem says, so let's take this limit. If n goes to infinity, what is that sequence going to go to? 0. The top is a constant, the bottom is going to infinity, so that goes to 0. So this theorem says since that limit is 0, then it will always be true that the sequence without the absolute value will also be 0. So let's see why that is. If we go back and look at that sequence, it bounced back and forth between a negative and let's be careful. One term it would be negative, the next term would be positive. The next term would be negative, then positive, then negative, then positive, then negative, then positive, then negative, then positive. Let's think about this. This was one sequence. This was negative 1 to the n, 1 over n factorial. If we look at the top half of that, isn't that going to 0? Because each term is getting smaller and smaller and smaller and smaller. If we look at the bottom half, it's negative, but isn't it getting closer and closer and closer and closer to 0? So by the squeeze theorem, since this one is going to 0, and since this one is going to 0, then isn't the whole thing really going to 0? The top and bottom halves are both going to 0. So anytime we have a series or a sequence that alternates, if when it's positive, if that goes to 0, then the negative ones will also go to 0. So by the squeeze theorem, they're both going to 0. So that's why they can say this. If the absolute value, if both halves of our sequence are positive, if those values are going to 0, then the entire sequence likewise has to be going to 0. If we take the absolute value, get away without having to redraw that. So if we take the absolute value at this point, we're maybe here, the absolute of that one would be like here, here, here. If we take the absolute value, if both sides are getting close to 0, isn't that absolute value getting closer to 0? So again, this theorem says if those are approaching 0, then the sequence as a whole is also approaching 0. All right, the next definition that we have is what's known as a monotonic sequence. Monotonic just means it's going in one direction. It's either always going up or always going down. So if we have a sequence that's going like this, notice each point is getting lower and lower and lower and lower. That's referred to as being monotonic. Likewise, if we had a set of points that were always going up, that's known as a monotonic sequence. So this one is said to be monotonically increasing. The other one is monotonically decreasing. Well, that's fairly easy to check at times. If I have a function, how do I check to see if it's increasing or decreasing? What about a function tells us if we're going up or down? X. The derivative. Remember, the derivative tells us the slope, and that tells us whether we're going up or down, increasing or decreasing. So if we have a sequence, we could take the derivative of that sequence, and that would let us know whether our sequence is always going up or always going down. If that sequence is always going to be a positive value, then it's always going up. If we take the derivative of our sequence and we get something that is always negative, then it's decreasing. Let's see if I can find an example. Yeah. If we look at this sequence, let's show that that's always going to be, that it's monotonic. So let's compare it to its corresponding function. The only difference is the domain. For this function, x can be anything but -1. For the sequence, n is only positive integers. If we take the derivative, that's the quotient rule, so 2 times 1 plus x minus 2x times 1 over the denominator squared. So that's 2 plus 2x minus 2x over 1 plus x squared. If we simplify that, we get 2 over 1 plus x squared. Isn't that always going to be positive for any value? The top is always positive. The bottom is squared, so it's always going to be positive. So this is monotonically increasing. Each term is going to be getting bigger and bigger and bigger than the previous terms. Now, another way we could show that, and for time's sake, we're not going to do it at this exact instance. Or are we? If this was the n sequence, or the nth term, the next term would be the n plus 1 term. So if we replace every n with n plus 1, if this is monotonically increasing, if it's increasing, that means every successive term is going to be bigger than the previous term. So that means the 2n plus 2 over n plus 2 is always bigger than 2n over n plus 1. So let's say that again. If this is our sequence, then this would be the next term in that sequence, because we're just adding 1 to each n. If it's increasing, then the following term is always bigger than the previous term. So we would just need to demonstrate that that's always true. Well, how do we do that? We would need to get rid of the fractions and show whether or not that's a true statement. Now, for time's sake, we're not going to do that right now, but we may do that in the future. There are one or two other things that we need to talk about before we conclude. So that's how we determine if things are monotonic. Either by looking at their derivative and seeing, is their derivative always positive, or is their derivative, that's supposed to be 0, always negative? So if the derivative is always positive, it's monotonic increasing. If the derivative is always negative, it's monotonic decreasing. Or we can just compare successive terms this way. So why do we care if something is monotonically increasing or decreasing? Well, I'm glad you asked. So let's suppose we have a sequence that starts up here, and it's always going down. If it's always going down, do you think that's going to converge or diverge? It seems like it would diverge if it's always going down. But what if we know there is some value that it never goes below? So this is always going down, but it doesn't ever go below that particular number. Is that really going to negative infinity? No. Look at an example. Several sequences we have done earlier. We'll just do this one. Aren't all of the terms getting smaller and smaller and smaller and smaller? If that's 1, then we got like, they're getting smaller and smaller and smaller and smaller, and they're always getting smaller, but they never go below what? They never go below 0. So if they are monotonically decreasing, and this bottom that they never cross is referred to as a lower bound. If we know there's a number that they never go below, but they're always going down, then they do converge. Now, we may or may not always know exactly what they converge to. But if they're getting lower and lower, and they're getting, and this is the bottom, usually that's what it's going to be getting closer and closer to. Think about horizontal asymptotes. Horizontal asymptotes apply to functions, but a sequence is just a special adaptation of a function. If we have a horizontal asymptote, if we're approaching that horizontal asymptote that way, aren't our points getting higher and higher and higher and higher? But do they ever get bigger than that? So they're monotonically increasing. That has an upper bound. So is that going to converge or diverge? It's going to converge. It's going to converge. Remember, when we did L'Hopital's rule, we did a lot of horizontal asymptotes. We didn't call them that, but remember, when you let x go to infinity, really what you're finding is a horizontal asymptote. You're looking as you go to the right forever, what are we getting closer and closer and closer to? The only difference is we have a sequence where, so our inputs are just integers. So again, if it's monotonically increasing and it has an upper bound, it converges. If it's monotonically decreasing and it has a bottom, a lower bound, it also converges. If something's not monotonic, if it's bouncing back and forth, the only time that something that's bouncing back and forth converges if both sides are approaching what? 0. If the top and the bottom are both getting closer and closer to 0, that would converge. But normally, if things are alternating back and forth, if both sides of the sequence are going to any number other than 0, then they would diverge.